What's up, scholars? Welcome to Pre-Calculus at Indianapolis Classical Schools. My name is Ms. Atkin, and let's get started. So we are all here to learn some pre-calculus. What is that? We know pre means before, so we're learning some before calculus stuff. So what is calculus? Well, calculus is interested in taking a look at functions and seeing what the slope is at any point on that function. That's called the derivative. It's also interested in all of the area underneath a function, maybe up to a certain point, maybe to the point where we took that derivative. So that area under the curve is called the integral. That's calculus under that shell. We're going to talk about pre-calculus. What do you need to know to start understanding integrals and derivatives? So we're going to start off with talking about functions. There's all different kinds of functions, but it turns out they kind of fall into certain categories. And we call these categories the parent functions. Okay, so we're going to talk about 12 parent functions. So I split my little piece of paper up here into 12 parent functions. Though I'm realizing I didn't give myself a whole lot of space here, so if you would like to draw yours a little larger, I would say go ahead and draw them a little larger. We're going to need a space for the equation up at the top. So the very first we're going to talk about is y equals x, the relatively boring linear function. And then we're going to draw just a quick little sketch of what it looks like. And then we're going to leave a space down here at the bottom to talk about the domain and the range. We're actually going to draw out all of the parent functions first, and then we'll come back to talking about their domain and range. So go ahead and split up your paper in 12 spots. Draw your graphs in each of them. Blah, 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 blah. And again, leave yourself some space. Alright, so here are the 12 parent functions we're going to look at. Y equals x, y equals x squared, y equals x cubed, y equals the absolute value of x, y equals the square root of x, y equals the cube root of x, y equals 1 over x, y equals 1 over x squared, y equals a to the x, y equals log base a of x, y equals sine of x, and y equals cosine of x. You may want to pause the video right here so you can write those down. After you do that, we're going to go to Desmos.com and do some graphing. Alright, here we are at Desmos.com. I have to start because I'm all up in this website all the time. Let's go hit up that graphing calculator and start our investigation of these parent functions. Okay, so we said the first one was y equals x. Should type it in the box would work. Y equals x. Who is that? That's a line. So all I want you to do right now is sketch that graph on your paper. Cool, that's your linear function. Now we're going to talk about y equals x squared. That's our good friend, the parabola. That's a quadratic. You've been knowing that for a minute. How about y equals x cubed? Okay, well that goes up to the right and then down to the left. Excellent, very cool. Make sure you're putting your arrows up at the top and the bottom of your graph to indicate that these are going on forever and ever. That'll be important when we talk about range and domain. Okay, next we've got the absolute value of x. Ooh, it's this nice, pretty V that's happening. And again, put those arrows on the end. Awesome, cool. Then we're going to talk about the square root of x. Notice that starts at 0 and goes only to the right. So make sure that shows up on your picture. Now how about the cubed root? The cubed root of x. How do I even put that in here? to the 1/3, which is the same thing. So this is the same thing as the cubed root of x. I'm just not sure how to type in the cubed root into Desmos right now. So I know that the cube root is the same as x to the 1/3. That might be something that's useful later. But this is the cubed root of x graph. Looks a lot like the square root of x graph, except for it continues on to the left. Now, why is that? Square roots only have positive answers, right? But cube roots can have negative answers. Like, for example, the cube root of -8 is -2, because -2 times -2 times -2 is -8, right? The negative cube root actually exists. So, make sure that information shows up on your graph. Who's up next? It's the rational function of 1 over x. I just find this very beautiful. So this has an asymptote, a vertical asymptote here, and a horizontal asymptote here. It will never actually touch the y-axis or the x-axis. Why is that? Well, if we tried to put in 0 for x, we'd have 1 over 0, and we know we can't divide by 0. So that's not possible, right? We cannot put in 0 for x, so it will never touch this x or this y-axis. And similarly, there's nothing we can divide 1 by to get 0. That will never happen. 1 divided by fill in the blank will never equal 0. So we will never have a value here. So we have a horizontal asymptote right there. All right. So make sure that shows up in your graph. And put arrows on the ends of your pictures. Now how about y equals 1 over x squared. What happened here? Well, what was down below has now gone above. So because this is an x squared, anytime you square a number, that number becomes positive. So we are always only dividing by positive numbers. So we have a positive divided by a positive, which will always be positive. So all of our y values have to be positive numbers, which is why this part of the graph is above the x-axis. Cool beans. All right, now the power function. Let's do 10 to the x. Okay, notice that point showed up right here. It's kind of an important point. That will always be the y-intercept to these powered functions. 10 to the x, 4 to the x, anything to the x. When we plug 0 in for x, anything to the 0 power is 1. So we will always have this y-intercept of 0, 1. Unless, of course, we were adding something to this. But this is the parent function. So the parent function will always have a y-intercept at 0, 1. So again, make sure that shows up on your graph. You put a little dot there and say 0, 1 to remind yourself of that pretty important point. Cool. The inverse of the power function is a log function. So log base 10 of x. Again, if I don't put a number here, remember back to your Algebra 2 days, if we don't put a number here for the base, we assume that base is 10. So this is log base 10 of x, which is the inverse function of the function we just talked about, which I'm just going to put these up here so we can look at them together. And I'll show you that they are inverse functions because they are perfect reflections across this y equals x. Okay? We're not really looking at either one of these right now, so I'll turn both of those suckers back off. I just wanted to show you where that came from. We're looking at y equals log base 10 of x, which has the inverse, which has the inverse point here, 1, 0. That will always be its x-intercept. Okay, so I'll put that on our graph. La-di-da. Mark that point, 1, 0. So here we've got a an asymptote. This is going to get really, really close to the y-axis, but it will never touch it, meaning the value of y is going to continue to go down, down, down to negative infinity. All right, and then up comes some of my favorite, most beautiful functions, the trig functions. First one is going to be sine. So notice sine goes through the point 0, 0, and it's this periodic wave. Oh man, that's just some pretty stuff right there. So put that nice little wave line on your picture and mark that very important intercept at 0, 0. Whee! Woo! 0, 0. Great. And sine's buddy, cosine. So cosine has a y-intercept at 1, 0. So it's really the sine function just shifted. But it's going to go through 1, 0, and then still make those beautiful wiggles. Beautiful, beautiful wiggles. 1, 0. Fabulous. Okay, so you should have all 12 of your parent functions sketched out. You know, they're pretty rough sketches. I just put some important points on there, like the y-intercept for the a to the x and y-intercept for log base a for the x, and sine and cosine to remind myself that sine goes through 0, 0 and cosine goes through 1, 0. Okay, now let's take a little detour. We're going to talk about domain and range, and then we'll come back and describe the domain and range of these beautiful parents. Okay, so we're going to talk about domain and range of functions. Now, domain and range are words that not only math uses, they are found in other places. For example, domain could mean the area of territory owned or controlled by a ruler or of government. It's got definitions in physics and computing as well as mathematics, and came from an old French word about belonging to a lord. But for our purposes, domain is going to be all the possible x values. All possible x values. And range has a whole bunch of definitions too. In music, like your musical range. Something about photography, I don't know about that one. How far away something is. You know, but we are talking about the math version of range, which is going to be all possible y values. Okay, so these get confused by students all the time. All the time. One of the ways you might remember which one is which, think about them in alphabetical order. D comes before R and X comes before Y. So domain are all the X's and range are all the Y's. However you want to come up with a way for you to memorize, awesome. But try to get it in your head that domain is all the possible X values of a function and range is all the possible Y values of a function. Now let's talk a wee bit about notation. And we're going to bring you way, way back to your days of a number line. Okay, so let's put a 0 in there. Let's go -1, -2, 1, 2, and go ahead and put an open circle. Wow, super throwback, open circles. Open circle on a -1, and we're going to put a closed circle on 2, and then shade in between here. So the notation we're going to use to describe, this would probably be the x's, so the domain of this relationship here between -1 and 2. Remember that open circle means it can't really touch that -1, right? Can't touch this. Dun, 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 dun. Right, but you can touch the 2 because it's closed. Can touch. Like a fuzzy blanket. Very nice. Okay. Open circle, can't touch. Closed circle, can touch. The way we would write this, we would use an open parentheses for that -1. And we're saying it's going to go from -1 all the way up to 2, but you can touch the 2, so we use a bracket. Can't touch it, open parentheses, can't touch it, open parentheses, can touch it, bracket. Or another way to write this is that the value of x, or the value of x has to be between -1 and 2. So -1 and 2, leave a little space here, but it can't touch that -1. So this is going to be just less than, and it can touch the 2, so that would be less than or equal to. These are the two ways you can write your domains and your ranges. Okay, so I like this one better. I think it looks prettier. It's a little bit faster to write. Open parentheses means can't touch it. Close parentheses means you can touch it, or another way to write that is with your inequality symbols. So the equal sign for when you would have a closed circle. Okay, but this is just on a number line. That's not a function. We're supposed to be talking about functions right now, right? So how does this relate to a function? Okay, so let's go back to our good friend, the linear function, and talk about the domain and range of the linear function. Domain is all the possible x values. So we're looking for how does it behave in the left and right directions, right? That's x, left and right directions. Well, it goes down and to the left literally forever. So it never stops going to the left. And it goes up and to the right literally forever. So it never stops going to the right. So it goes to the left forever and it goes to the right forever. So the way we say that is the domain is from -infinity to +infinity. Now, why did I put these open parentheses and not brackets? Because you can't touch infinity. You're never going to get there, right? Infinity is a concept. It's not a number. So this is a can't touch this situation. How about the range, though? Now we're looking at the up and down directions. Well, we said this went up and to the right forever, so it means it goes up forever. So it's going to get all the y values eventually. And it's going to go down to the left, so it's going down forever. It's going to get all the negative y values eventually. So that means the range is -infinity to +infinity. Cool. All right, let's go check out our good friend, the quadratic, the y equals x squared. Okay, let's do domain first. So we're looking at left and right. What's happening in the left and right directions? Well, this guy is going to the left and up forever. So that means it's going to the left forever. So eventually it'll get all these negative x values. I mean, they'll be way the heck up there, but they'll negative. All the negative values are going to exist. And similarly, it goes up and to the right forever. So we will eventually get all these positive x values. So the domain, again, is -infinity to +infinity. -infinity to +, but again, we're using the parentheses. Why? Because you can't touch infinity. You can't touch it. It's too hot. What about this range, though? Now we're looking in the up and down direction. This does not go down forever, so we're not going to get all the negative y values. Just not happening. What's the lowest y value we have? Is 0. So the lowest y value we have is 0, and we do touch it. There is a point there, but then this goes up forever. So we will get all the positive y values. We're going to start at 0 and go to all the positive y values. That means our range does touch 0 and goes all the way up to infinity. Cool. I want to skip down to this asymptotic beauty, 1 over x. So let's check out the domain of this function. Again, we're talking about the x values left and right. We can see that we go to the left forever, so we're going to get all these negative x values, and we do go to the right forever, so we'll get all these positive x values, but something weird is happening in here. There are some asymptotes in here. Specifically, there's an asymptote at this y-axis. X will never be allowed to equal 0. Remember, we can't plug in 0 here. So we go from -infinity and get close to 0 but never touch it. -infinity, get close to 0 but we'll never touch it. And then we pop on over to the other side. We get really close to 0 on the other side, but we'll never touch it, and then we go to positive infinity. So what this means is our domain goes from negative infinity, close to 0 but doesn't touch. So negative infinity, close to 0 but doesn't touch. And union, you put a U there, it's a U symbol. If you have space to do this all in one line, awesome, but I do not, so I'm going to have to do this kind of broken up a little bit. We go from negative infinity, close to 0, never touch it, and then we go on the other side of 0, still not touching it, and go up to positive infinity. So we're negative infinity, comma 0, union 0 to positive infinity. Okay, so again, if you have space to write that all in one line, better than I do. Cool. Now let's talk about the range, talk about the y values. We see we go down forever, so we're going to get all the negative y values, and then something goofy happens again here at the 0. We will not ever touch 0 in our y values, and then we skip over, and we go up to positive infinity again. Why do we never touch the 0? Because we can never divide 1 by something to get 0. We will never be able to plug in any number for x that will give us a 0 for y. So 0 does not exist in the range of this function, which means our range is the same as our domain in this case. We go from negative infinity to 0, not touching, union 0 to positive infinity. Okay, and now let's skip down to my good friend sine of x. Here they are, sine of x, doing their beautiful, lovely, wavy thing. Let's talk about that domain. What's going on here? Looking left and right, left and right, left and right. Looks like we go to the left forever and to the right forever. There's no place where it's stopping. So our domain for sine of x is negative infinity to positive infinity. Awesome, awesome, awesome. Okay, range. Looking at y values, up and down situation. Definitely doesn't go up forever, definitely doesn't go down forever. It's got some bounds here. What's the lowest y value we ever get to? It is negative 1. And what's the highest y value we get to? It is positive 1. Sine always stays between negative 1 and positive 1, and it does actually touch it. That point truly exists. So that's going to be some bracket action. So the range of values here is from negative 1 to positive 1. Or if you're into that other type of notation, we could say negative 1 is less than or equal to y is less than or equal to 1. Again, we're using the equals to because it does actually touch. Okay. For you to finish these notes, you're going to find the domain and range of all of the rest of these things. Cool? Cool. If you are getting really stuck and you cannot figure it out from the graph, use the internet. You want to Google the question you're looking for. What's the domain and range of y equals log x? And you go down and click on some links until you find something that makes sense to you based on the knowledge that you have. That looks like the thing I'm looking for here. Okay, cool. Oh, look, there's interval notation. The domain of this log of x is 0 to infinity. It's got the open parentheses. Cool. Tells me the range, negative infinity to infinity. Awesome. Great. So, your mission, which you will of course choose to accept, is to find the domain and range of the remaining functions. Once you have done that, you are done with your notes about these lovely, lovely, lovely parent functions. And you'll snap a little picture, send it in for points, bada bing, bada boom. That's it, scholars. You have survived lesson 1 of pre-calculus. Nicely done. I'm so proud of you. I love you so much, and I will see you next time.